You've got a problem with my new hairstyle. You're just going to have to deal with it because the man bun is approved wear in HTM school. Hello again and welcome to HTM School. My name is Matt Taylor from Numenta. Today we're going to start talking about encoders. Now, you can think about encoders as roughly equivalent to your sensory organs when we're talking about HTM systems. How do we get data from the real world into this SDR format that we've been talking about so that an HTM system can actually process it? That's what encoders do. Some examples of biological encoders are like your retina or your cochlea. These take stimulus from the environment and somehow translate them into a stream of SDRs that are like neural activity going into the brain. So each one of these hairs in your cochlea responds to some frequency range of vibrations that are occurring via sound. And as those activate its neuron, it turns into a part of an SDR that's passed into the brain for processing. So we're going to talk about scalar encoders today, and we're going to use a similar technique as the cochlea, although it's going to be much, much simpler than the cochlea. So let's look at an example. So talking about encoding scalar values. First of all, let's go to N and W. This is the dimension of the SDR that we're going to produce, 400 bits, 21 of which are on. That's pretty simple. I'll talk about this bucket value in a moment. We also have, importantly, a value that is going to be encoded. That's what this slider represents right now. This is 50. You can see this is the scalar encoding of 50. Now, as I move this slider up and down, that scalar encoding changes. You can see how that bar of on bits within the representation is moving up and down. We also, you might notice there's a minimum and maximum value here. So we do have to specify the min and max value to do this type of scalar encoding. So I could make this very large, and then the encoding for 54 as it is right now moves higher up or earlier in the array that we're creating, and we can move it just like we did. Now we're spanning a much greater value, so our range of values has increased quite a bit. We can also change the amount of bits we want in our encoding. Now we're dealing with a much larger encoding of about 1580 bits. The scalar value encoding changes as you would expect it. Let me show you some things as I move this along. I'm going to turn this comparison switch on so we can see as I change the value the difference between these values. So in this case, I've got an encoding. The last value that was encoded is 429. The current value is 430. So you can see from here to here is 430, right? And from here to here, that's 429. So the difference between the value is basically that these couple of bits moved from one side to the other, but they are semantically similar. They have a significant amount of overlap here, so that's what makes 429 similar to 430. If we move up a little bit farther, like here I moved from 430 to 473, there's no overlap at all between these two representations. So there's going to be no similarity at all between those. Now you can have some control over this. So if I make my W bigger, and that's essentially the bucket size, I'll talk about buckets in a minute, then my overlap is generally going to be bigger, and I can represent differences between larger ranges. Like for example, here's a comparison of 467 to 509. The lower value is the yellow bits and the red bits. The higher value is the red bits and the green bits. But there's still some overlap here between these two values that are pretty far apart. So when you're tuning scalar values, you can decide exactly how you want that encoder to work on your numbers. So let me refresh this. So if we want to have a very small range of values that we want to represent here, we can do that. And now from 42 to 100, that's what we're encoding, and we can change this bucket size so that those are very similar, as you can see when I turn the comparison on. They're very similar between values, right? Or we could make this bucket size much smaller. We could make the overall dimension of the SDR much smaller and get it to a point where we have exactly the resolution we want when we're comparing values. So in this case, the way I have it now, one integer's difference, of 87 to 88, does not have much overlap at all. Maybe that's what you need with your data, maybe not. If you want to have a lot of overlap, you want to make the bucket size bigger, and then you'll get a lot more overlap between these values. So about the bucket size, by the way, so when we talk about buckets and encoding, I'm talking about this shape right here. This is one bucket. And it's basically, for the scalar encoder, it's a consecutive array of on bits of exactly 21 length currently, because that's what I have set here. So given that we want a bucket width of 21, I can fit 380 of those in this space. And you can sort of see that as I move this. Here's the first one, 2, 3, 4, 5, blah, 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 all the way down to the bottom one. There's 380 ways that I can put those consecutive on bits in this space. If I make the bucket size larger, there's less ways that we can fit this in the space, right? If we make the overall SDR size larger, there's lots more ways we could fit that many buckets in the space. So when we're talking about buckets, we're essentially talking about a representation of on bits where we can represent different values, one or many values. So let's talk about periodic encoding as well. So I'm going to make this bucket a little bit bigger, so to illustrate this, I'm going to turn periodic on. And you might have noticed in earlier in this example, when I got to the very limits, the minimum and maximum scalar limits, that the representation didn't change. It stayed at the minimum, even though I went much further down. And you can see that here. I'm in the negative ranges. The minimum is 0. It doesn't change the representation. It maxes out or mins out at 0. Same thing if I go above 100, it maxes out at 100. Any values outside of the range you specify gets clipped and is represented as the min or the max. But we can tell it we want a periodic representation, in which case when we get to the maximum, it doesn't clip, it wraps around to the front of the array. And when you have this, it's sort of a cyclic representation. We're going to talk about this when we talk about date encoding soon in the next episode. But a date encoder, when you have hours from 0, 1, 2, 3 all the way up to 23 or 1 to 24, midnight is very similar to 1 a.m. So the 24th hour in the day should be semantically similar to the first hour in the day. So that's what we need the periodic encoder for, so we can represent that. So in any case where a range of data wraps around itself, then we want to use this periodic aspect of the scalar encoder, so the minimum values are semantically similar to the maximum values. So now let's talk about another type of scalar encoding. This is called the random distributed scalar encoder. It essentially does the exact same thing as the scalar encoder, but it does it in more of a random distributed fashion. So instead of having these buckets of consecutive on bits like we did in the previous one, so you might have a whole section of on bits to represent one bucket. In the RDSE, that on bit section is hashed out and distributed randomly through the space. So in this case, this is representing the value 500, and we can also again change the representation that we're creating here, increase the number of bits that we want. Just set it back to what it was. But the interesting thing here is as we increase the value, 505, 506, 507, 508, you see those bits? There's one bit that's moving between these buckets. So every time we change a value, and now you can see it really clearly, there's a bit that changes. So every bucket has one bit difference between its left hand and right hand buckets. So we have a resolution right now of 1. That means every bucket is going to get one value. So every time I change this value, it gets a new bucket. Every bucket represents one value. So if I up this resolution, I'm going to bump it up all the way to 5, and I'm back on for the value 560, for example. Here's what we see. Go to 561, No change. 562, there's a bit difference. 563, 4, 5, 6, all the same bucket. All those values are being represented in the same bucket. We go to the next one, we finally get a bit change. So these buckets have 5 values in them. So the semantic similarity is completely the same between, for example, 556 or 566 and 562 in this example, which might be fine for your input data. Maybe that's a small enough granularity that they might as well be the same. It depends. But if we go to a much different value, we can see there's an entirely different representation. In this case, we just went from 366 to 410. We can see exactly how much overlap we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 or 12 bits of overlap. So, and we can tweak these numbers, the width of the bucket, the size of the distribution. Generally, we want a very high N and a W that gives us enough on bits, but also enough sparsity. So a couple of things about the RDSE. First of all, it requires state, which is a little interesting. The scalar encoder did not require state. It could encode something without any state at all. It needs as an input value, some easy algorithm, and it will produce the output. For the RDSE, we need state because, and I'll show you here, watch this bucket value. It only says it has 2 buckets right now, and that's because it's only seen these 2 values. And as we go up, it's going to continue adding buckets. It grows as it sees more data. The RDSE has to keep track of the different buckets it's already randomly created, so it knows if it sees a new value where it needs to start creating more buckets. So it kind of grows on either edge. Watch when I pick a value that's over here off to the side. You'll see that it's suddenly, now it's got 261 buckets in it because I just jumped all the way up to about 260 something value, so it needed to run through all of those different buckets, creating them all so we could get to this representation. So the RDSE kind of dynamically expands in each direction. You don't necessarily have to provide it with a minimum and max value as explicitly as you do with the scalar encoder, but you do kind of have to have an idea about the resolution. How many values do you want to fit into a bucket? So I've been using integer values for all of these encodings. Both of these encoders handle decimal values just as well. I'm just not showing that example. For example, if I take the resolution below 1 or between 1 and 0, you'll see as we turn this comparison on that there's more than one bit that's changing between buckets because there's more than one bucket being created between these 2 values because it's making room for to store the values in between the integers, right? So if the resolution is less than 1, we're expecting to store decimal values. So we could go to a very low resolution here to store those types of much smaller numbers and still get the same resolution and semantic similarity in the encodings that we're creating. So that is the random distributed scalar encoder. So these are not the only methods of doing number encoding for HTM systems. These are 2 of the most commonly used in our current systems, but there's no reason you can create your own scalar encoder or numeric encoder as long as you follow these 4 principles that I'm going to talk about in the next episode on encoders. Let's take blood pressure, for example. Blood pressure is a reading that consists of 2 numbers, the systolic and diastolic blood pressure. Now, these 2 numbers sort of depend on each other on how they should be interpreted. You can't interpret a blood pressure with just one of these numbers. There's a semantic meaning for the pairing of these 2 numbers. Like, for example, the range between the systolic and diastolic numbers in your blood pressure is called your pulse pressure. If your pulse pressure is too low, that could mean that you have congestive heart failure or that you're in shock. So that's a potential encoder, a blood pressure encoder in itself. The encodings of these individual values do not contain the necessary semantic meaning unless they are paired together and the relationship between them also gets encoded as well. So there's lots of opportunities here for the community to create new and interesting encoders that take that real world data and encode that semantic meaning for that specific domain. In the next episode, we're going to talk about the date-time encoder and how encoders that are encoding different semantic meanings in different parts of the data can combine them all into one encoding that represents all of the things it wants to represent at once on the same playing field. So stay tuned for that episode and take care. Thanks for watching HDL.